Okay, I'm started now, and I'm just going to try to open some windows. All right. Okay. Windows again. I got that one. All right. Let's open. Another. I'm gonna try to see if I can get another file up here. All right. Desktop. Thermo's running. All right. Here. I see that now. Okay. Okay, hello class. I hope everyone is doing well and staying safe. This is my first attempt at recording a lecture with the tools we have available, and I can warn you right up front that I'm not very good at it. And hopefully as I do more and more of them, I'll get better. I also, you'll notice I'm not looking directly at you. That's because I've got a laptop over here, and then with a small screen, then I've got my big screen on my desk right here, and I'm looking at my big screen. Now, if I look back this way, I'll be looking right at you, but I can't see the big screen, and can't and won't be able to do nearly as good a job if you can call what I'm doing a good job. Okay. So I hope that's not too distracting to you you're looking at me from the side. I don't think that's even my best side either. But anyway, um, again, I'll fumble through this. I'm going to say a lot of uhs. I'll be clearing my throat. I'm just not used to doing this online, and it's been a struggle. But everybody that teaches pretty much in the country is doing something like this. So I'm certainly not alone. So I don't believe I'm justified in whining much about it. But anyway, bear with me and hopefully we'll get better, or I'll get better. Now I'm going to start. We're at chapter 5. You either have taken the test on chapters 3 and 4 or will be soon. I hope you do well. Chapter 5, and let me also say I'm going to have to go over slides a good bit. I was hoping to simulate using the blackboard, but as I show you, you know, the way I like to present to you is to have the projector with the slides, and then have the blackboard over at the left side where I can do sketches and so forth on it. And my theory is that breaks up the monotony of just looking at slide after slide and me reading bullet point out after bullet point. I even went out and bought a nice Wacom tablet to try to simulate the whiteboard part of my lectures. Well, the tablet works fine, but getting used to writing on a tablet that's down like this and then having it show up on your screen up here, right down here and showing up here, is a lot more difficult than I thought it was going to be. And I cannot write fast enough on this tablet to be useful. But maybe I'll get better and we can use it. So, and maybe it'll break up monotony. But anyway, let's try to get started here. All right. I'm going to move my, in this video, you see that noise, that visual noise on the left and right side? It looks like a swarm of blackbirds or something. I don't know what that is, and I'm sorry about it. It wasn't here yesterday, but it is here today. So if I put this back, my face and down in here, sort of in the corner, maybe you won't notice it. And you'll see me getting what you see. I don't see exactly what you see on the screen. And that makes it difficult for me to make sure I have the right screenshots displayed for you to look at. So you'll see me going around with a cursor and trying to make sure I'll try to be hitting this. You can't see it. I'll be hitting the share button up here to try to see that you're sharing the right screen. In other words, not that screen, but the screen I want to share with you, and it disappeared. There it is. That screen. Maybe it's this screen. It's just really hard for me to get started. Hard for me to manage. Okay, here we go. Chapter 5, the second law of thermodynamics. You remember the first law was the best way to say it is energy conserved. E is conserved. And you remember we got this equation. See if I can go to that equation. All right, I wrote this equation out on this new board. By the way, this my new Wacom board. If I go, I can write on this board pretty well. But again, doing it fast as I would with a regular crayon and make it look half as good as so far has really been impossible. But I did write this equation here, and let's see if I can put my pen down. Okay. No, we're going to need to stretch it out, aren't we? This is just really, really hard for me. Sorry. All right, but this is the first law equation written in this form, in many forms you can write it in. That says sum of all the energy streams entering, and each energy string is a m dot times enthalpy dot plus velocity squared over 2 plus g times the height or z dimension. So that's potential energy, kinetic, and that's the main energy we deal with, which is the fluid energy. So this says that the sum of all those exiting the control volume minus the sum of those similar streams entering the control volume, I for entering, is equal to the heat transfer of the control volume minus the work of the control volume. These are all rates. You see the dots on. I mean, that's heat transfer per minute, second, or whatever, and work. It could be, now if I say kilowatts, that is per second implied. But if I said joules per second or horsepower is also the rate of doing work, so that takes into the dot, but BTUs per minute would need to have the minute. So those are all dots. Now, if I simplify this down to one stream entering and one stream exiting, which covers many of our problems, I'm left with this equation. And if the velocity goes away, and we don't have to consider velocity, then this term goes away, and you're just left with H2 minus H1. So this now is the fluid energy term, and this is the kinetic energy term. Usually this is less than 1% of this, so we can ignore it. But on the test, I'm going to give you a problem like this, and I want you to be able to handle this little calculation. Okay, so if it's if the velocities are small enough and we ignore them, I should be able to take my pen here and erase it. This actually works decently to erase this. That's what I do on your board. Erase the plus sign. Oops. All right, but now if I try to redraw that parenthesis thing, it's just really hard to do, I'll tell you. Now, if we're talking about a turbine and we can neglect heat transfer, then of course this term drops out. So anyway, you see how that works. It doesn't, let's see how the arrow works to get it back in. Okay, that's pretty good. All right, so if it's like a boiler where the heat transfer, where there's no work, then this term goes out. And let's see if I can lasso it. By the way, I'm using how do you do it now? Hit the delete key. No, I don't know. Like I say, I'm really struggling with this. All right, I apologize for all of this wasted effort. So if we were talking about a boiler, that term and the velocities were pretty equal on the inlet and outlet ports, we could leave that off. And if it were a boiler, okay, then this would go away and you'd be left with that. And if it's a turbine, this would go away and you'd be left with that equation. Okay. But the important thing in the second law I was going to mention, this energy equation, or the first law equation, it doesn't say anything about how much. It says that energy, it's either got to be here, 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 here. It can't disappear and you can't create it. it has to be accounted for in this equation. But what the first law doesn't tell you is how much of this fluid energy here, are there any limits on how much of this fluid energy here is converted either into work or either into heat? No, you could have all of the fluid energy converted into heat or into work. That would be, all right, I'm going to attempt to do another drawing here. This is probably going to be trouble. Let's go up here. All right, let's draw a boiler. Oops, I'm still here. I got to select this pen. All right, I'm going to hit the share button and make sure I'm sharing you with. Yeah, okay. You are seeing what I'm seeing. Okay, should be. All right. Well, let's take some of this out. Let's just take it out. Hit the eraser. Whoops. Oh, I got to do it with a pen. Sorry. Just get rid of it. Like I say, I hope I get better with this thing and can really use it to simulate. Now try the lasso again. That's with my right hand. I'm doing the mouse now. All right. Now should be able to cut that and it disappear. Okay. All right. I'll try to draw it. Let's say we have a boiler here. Oh, gone it. Select the pen. Now, let's say I have a boiler here. And there's a lot of heat transfer, flame, natural gas, coal, and there's some heat coming in here. We usually give the term QH. All right, it's coming into the boiler. Watch this. I'll mess this up, I'm sure. B-O-I-L-E. See, I got a long ways to go. Now we go over to the turbine. Try to draw it the way I usually do with expanding sides. This is the turbine. All right, of course it had, whoops, I don't know what caused it to do that, but it does. So we have the shaft here and we have power coming out of it, driving a generator. Now out of the boiler, we get hot, high pressure steam comes into the turbine here. And out of the turbine, it goes through and expands and comes out. It's still hot, relatively speaking, but it's lost most of its energy, not all of it, as we'll see. And it's hot, mostly steam, maybe have a quality of 95%. But here the pressure might be, let's see, 3,000 divided by 15. That's 200 bar. It never goes up that far. Let's say 100 bar. And that's a high pressure. See how it's really, really difficult. 100 bar coming in pressure. And temperature, maybe 600 degrees C. Really hot. Hot, a lot of pressure. By the way, 100 bar times 15, that's 1500 PSI, and that's also 10, actually it's 1450 PSI, because anyway, sort of beside the point. Now when it comes out of the turbine, it's very low pressure, say 1 bar. I hope you read my script. 1 bar. And the temperature is probably down some, maybe, I don't know, 400 degrees C. All right. But let's say up here that we're putting in the QH. I don't have room up there. Let's say we're putting in 100 units of heat. Now, that could be 100 kilowatts, 100 let's see, 100,000 BTUs per, by the way, that's a rate too. Put a dot over it. But let's say it's 100 units a minute. Now, the first law doesn't say anything about how much of that we could convert to work. You could say, well, I got 100 units of heat in here. I can go through this turbine, get out 100 units of work. Well, the second law of thermodynamics tells you that's impossible. For one, it tells you that you cannot have a device that's accepting heat from one source, QH, and producing it, all of it into work, without some of the energy going back out. It just said, well, it just says you can't get in 100 units of heat here and get a, sorry, whoops. Let me check the share and make sure you're still seeing my, yeah, okay, you are. All right, you can't get out of, doggone it. It's my palm. I got to figure out how to disable the palm. You're not going to get out. The first law doesn't say you can't get out 100 units of work. So, but the second law says essentially you cannot do this. You cannot take heat from one source and turn it all into work. Some of it's going to be rejected and going to end up flowing back around devices and coming in here. Actually, what would be a good number? Now remember, heat and work can have the same units. We generally think of work in kilowatts, but we also think of heat in kilowatts. So it's energy. You're putting in 100 units of heat, energy in the form of heat. How much can you get out in the form of work? Well, the second law is going to tell you certainly, I'm sorry, I hit up. You're certainly not going to get out 100. In fact, in a real generating plant with a big steam turbine, let me see if I can erase that. You're probably only going to get about 35. So for every 100 units of work, you'll be doing pretty good to get out. No, for every 100 units of heat, you'll be pretty good getting out 35 units of work. But remember, heat energy tends to be pretty inexpensive. Natural gas, fire boiler, electric boiler. Heat energy is just easier to obtain. It's less expensive. And the work output, this torque and speed that's driving the generator, that's really high class energy. That's what you're after. And it's probably very true that if you can pay for 100 units of heat and get out 35 units of work, you're doing very, very well. You're probably making electricity at some number like 4 cents a kilowatt. But the thermal efficiency you're getting, no, all right, let's see if I can write that now. That's supposed to be an eta, T for thermal. That's pretty good T there. Is equal to the work out, call it work net, over this QH up here. Now, talking about a power cycle, why did I say work net? Why didn't I just say work, like over here? Well, I don't show it in this, we'll see it later, but I also have to drive a pump in this circuit. Pump some water back up to the boiler. This water is making the trip all around here, and I don't show a couple other devices. So there is some work more work that has to be paid for, and that's the pump work. But it's generally less than about 1% of the turbine output, so it's not a big deal. So the efficiency of the cycle is essentially the work net over, and that in the case we just talked about, 35%, sorry about that, would be a pretty good number. All right. The second law tells us you cannot take all these 100 units of heat and convert it into work. By the way, a couple of things I want to mention about the second law. There's no real easy way to say the second law. The first law, you can say energy is conserved, or the energy is converted from one form to another according to the energy equation. You can say it in a pretty nice, concise form. You can't do that in the second law. It's several statements on the second law. There's we'll get into them shortly. But there's no easy, concrete, one sentence way to the second law. One corollary or one aspect of the second law is you cannot take 100 units of heat and convert them into 100 units of work. That's one way. All right, let's see if we can go back to PowerPoint screen here. Uh-oh, I think I just closed it out. I did. All right, let's see if I can get it back up. Here it is. I want it to be on now. Let me look at share again. Okay, go back to the screen. They all show up. I'll get the hang of this eventually. All right, so everything we talked about is still here, the screens. All right, now we're going to focus on the PowerPoint screen a little bit more. Now, I can't take the screen and make it, put it in the presentation mode where the PowerPoint slides cover the whole screen. If I do, it looks like I can't get back to my video control. So I won't be able to do that. So hopefully you can see this well. By the way, after you look at this video, send me your comments on things that worked and things that didn't work. And I can't promise you I'll know how to correct them, but I'll try. All right, Chapter 5, Second Law of Thermodynamics. Let's get going. Okay, what we're going to try to learn in this Chapter 5 is the key concepts related to the second law, and I apologize in advance for reading this to you. There's just no way. I'll try to ad-lib as much as I can to make it not so dry, hopefully. There, like say, what this means, explain key concept. There's several ways things involved in the second law. There's several statements of the second law. We'll talk about internally reversible and irreversible processes. The Kelvin temperature scale. We've already mentioned that. Let's see if I can get back to the, let me take this out. I'm using you as guinea pig, try to get reasonably good on this sketchboard. Let's take the lasso up here. Well, it didn't, let's see if we can get rid of some of that. All right, we can use a eraser on that, I guess. No, have to use my pen. See, I'm using my mouse some and my pen here. Here's my, all right, go over here and erase that. Now, this is what getting old is all about. I forgot what I was going to show you. I was just going to write down that the Kelvin temperature, we don't put a, all right, got to select a pen, Larry. K, we don't put a degrees after it. I don't know why. Is equal to degrees C plus 273.25 or 15. I can't remember which it is. But we use just 273. That's fine. And when you're dealing with a second law, you'll need to use absolute temperatures like Kelvin, sort of like working with ideal gases. And we know that in degrees, Rankine in the English system, and we are allowed to put the little degree symbol there, is equal to the 460, should have put the plus whatever you got in degrees F. It's a fine looking F, would you say? Looks sort of like a stick man that's about to fall down. But anyway. Okay, let me see if I can get back to the PowerPoint screen. I'm getting a little better at it. All right, whoops, lost it. I deleted it again. Oh goodness. Oh, there it is. Came back. Let me make sure and see what you're seeing. All right. Okay, we're back where we were. All right. And we're going to talk about irreversibilities. Irreversibilities are, I like to think, that's just power losses, like in the internal combustion engine. What are some of the irreversibilities? How is some of the power inside the gas, the potential loss? Well, friction is the main one. Heat transfer is another. You know, an internal combustion engine is only about 40% efficient. If we could, so about 40–50% of the gasoline power is lost in the form of heat. If that's an irreversibility, if we could convert that into work, it'd be good. But an internal combustion engine, like I mentioned before, you know I'm interested in those, is that number one, you're compressing the gas or the air, which is 95%, 98% air and 2% fuel. You're compressing it, and as you know from being a good thermo student, anytime you compress it to get a higher pressure, you get a higher temperature as a side effect. So you end up with when you compress your gas in the cylinder, it gets hot. Then you're going to put a flame on it with a spark, and so it's going to get further hot. So that's why so much of that, you have so much heat. All right, so let's keep going here. All right. We're going to evaluate the performance of 3 different cycles, and I think it's sort of interesting. Power cycles, which we just mentioned, that's to produce electrical power. Refrigeration cycles, that's to cool our food in our refrigerator, or freeze our food in our freezers, or cool ourselves off when we're sitting in a nice air-conditioned room like I am. And then heat pump cycles. Well, heat pump and refrigeration actually use the same components in their cycle, the same working fluid, the R134A refrigerant, or the, what is it, R410. So they both use the same fluid and they use the same components. It's just running, one runs backwards to the other, but we'll talk about that. Then the Carnot cycle, which was developed by who? Yeah, Mr. Carnot, you're right. And when he did, he came up with the most efficient thermodynamic cycle possible. And he reasoned out that it was dependent on the TH, the temperature of your hot reservoir, where you're getting the heat from. And then the ratio of that to your TC, or T cold, where you're ejecting the heat that you cannot turn into power, where you're ejecting it. Those 2 values, TH and TC, and we'll see that, or limit you to the maximum power you can get in a refrigeration cycle, but more importantly in a power cycle. And we'll talk about the Clausius inequality as a measure of the second law later. That's all right. Okay, let's go to slide 3. All right. Here are the aspects. Now I've covered some of this, so I'm reading it to you, but I don't feel too bad because I've tried to explain it to you in beforehand. But from conservation of mass and energy principles, we know that mass and energy cannot be created or destroyed. For our process, conservation of mass and energy principles indicate the disposition of the mass and the energy. In other words, fluid energy converted into heat and or work, but it does not tell you, does not infer whether the process can occur or not. For instance, if I tell you I've got a turbine that converts 60% of the fluid heat energy, fluid energy, the enthalpy, if you will, I've got a turbine that converts 60, 70% of that into work. Some turbine salesmen tell you that. Well, you can't take out the first law equation and prove them wrong, but you can take the second law and with the TH and TCs, you can tell them just with a simple calculation on the back of an envelope whether it's possible or not. So the second law of thermodynamics provides a guiding principle for whether a process can actually occur or not. Now, aspects of the second law, slide 2 or 3. Like I said, the second law of thermodynamics has many aspects or many corollaries or many bullet points or many statements. It's not one tight little sentence. But among the aspects of the second law is they do predict the direction of a process. In other words, heat can flow from hot object to a cold object, but the second law says it cannot flow from a cold object to a hot object. And you might be thinking, well, what you mean, Mr. Ezel, air conditioning, you are all the time taking heat out of a cold room and rejecting it outside in a hot environment. Well, you are, but you're putting a lot of work into that compressor to get it done. The aspects of the second law, conditions also establish the conditions for equilibrium. And like I said about the Carnot efficiency, they tell you what the best theoretical performance of cycles, engines, and other devices. Evaluating quantitatively the factors that preclude attainment of the best theoretical performance level. In other words, we can predict the best performance level. We can't take the second law and predict what the performance of say, a refrigeration cycle is going to be, but we can take the second law and tell you what the best you can possibly get is. And most of the time, the best you can possibly get is much less than the maximum according to the second law. In other words, the second law says you can get 80% efficiency, in the real world, you're probably going to get about 35 or 40. Okay, like I said, there's no simple statement to capture all the aspects of the second law. Several alternative formulations of second law are found in the literature, which we're going to go over. The prominent ones are the Clausius statement, the Kelvin-Planck statement, and the entropy statement. We're going to cover each one of those. The focus on chapter 5 we cover now is the Clausius and Kelvin-Planck statements. We'll mention the entropy statement in chapter 5, but I think I'm going to go get me a drink of water. I'm going to see if I can stop the video. Okay, hopefully I'm back. You can see me now. Let me check my share again. Make sure you're seeing the screen that I'm seeing. Yeah, according to that, you are. All right, let's keep on going. Like I say, our emphasis will be, by the way, the Clausius and Kelvin Planck statements are only, and the entropy statement we'll get to later. These are about the only things that you have to memorize in, I'm going to try to look at you while I talk now. These are about the only things you'll have to memorize in this course. And you don't have to remember it word for word. You're going to have to write on your test what those two statements say. And if you get a is instead of or get a minor letter, that's fine. I just want you to understand what they mean and be able to write out what they mean in 3 or 4 or 5 sentences such that I understand that you understand what you're talking about. All right, I'm going back to look at my big screen again. Okay, let's scroll down, go to the next. Okay, here's the statement of Clausius. It's really quite interesting. It is, and this is what this in blue here, that's what you, let me see if I can do the annotate. Okay. All right, this in blue here is what you'll have to write on your test. It says it is impossible for any system to operate in such a way that the sole result would be energy transfer from a by heat from, oh, I wish I knew the editor. I'd go back and edit that out. Let me try again. It is impossible for any system to operate in such a way that the sole result would be energy transfer by heat from a cooler to a hotter body. Now, where does that shows up in air conditioning and refrigeration heat pumps? Because that's what we do. We transfer for a freezer. You're transferring heat. You're pulling heat out of that cold refrigerator and dumping it out in an already warm room. That says it violates the Clausius statement. Well, it does, but the reason it's not a violation is because that's not the sole result of how your system is operating. You got a compressor and some other stuff in there. So this is very true. It is impossible for any system to operate in such a way that the sole result would be energy transfer by heat from a cold to a cooler body to a warmer. All right, let's take that off. Now let's look at this down here. So this shows heat. This is a hot body up here, and let's say a rod between a hot brick and a cold brick. We got a metal rod, a highly conductive metal rod, say a copper wire, copper rod. Well, copper rods, as you electrical engineers know, they conduct electricity, electrons very well, but they also conduct heat. In general, anything that conducts electrons well also conducts heat. But let's say we got a hot body up here and we got a cold body down here, then absolutely we can transfer heat from this hot body down through this rod to the cold body. Yes, sir. But what Clausius says you can't do is you can't go from this cold body and transfer heat back up here to the hot body. We do it with air conditioning system, like I said, but there's a whole lot of more stuff you have to add in, and you have to put a lot of energy in it to get it done. Okay. Clausius statement of the second law. All right, let's go to the next slide. Annotate. I want to take that off, don't I? Get back to my cursor. Okay. Now, what is a thermal reservoir? In this abstract drawing here to demonstrate this principle, we sort of have a thermal reservoir up here, a hot one, and then a thermal reservoir down here. What is a thermal reservoir? A thermal reservoir is a system that always remains at constant temperature, even though energy is added or removed by heat transfer. Now, we always think of the atmosphere as a thermal reservoir because most man-made thermodynamic systems. Now I know about global warming and all this stuff, but that's a little bit outside of what we're talking about. By the way, this recording is going to end in a few minutes, and it probably end rather abruptly because I got a timer on it. If it does, don't worry, I'll be back to finish the chapter in another recording. And by the way, I intend to put these both up on YouTube, which I haven't done yet, so I don't know. Anyway, I'll tell you where they are and how to get them. So thermal reservoirs, we think of the outside atmosphere, especially in in an air-conditioned situation, because we're running an air-conditioned system. We're taking heat out of the inside of our houses and pushing it out to the outside. And we don't think of it having it's not enough energy to have any effect on the to change the temperature of the environment. For instance, if it's 90 degrees outside on a hot day at my house and I've got the air conditioning running and it's taking heat out of the there's all kind of heat coming in from the walls and the windows and so forth. That tends to make the inside temperature go up, but the air conditioning system senses that, turns on the system, and actually pulls heat out of the room and dumps it outside. Well, it's still 90 degrees outside, and unless you get within a foot or two of that outside unit, you're not going to feel any difference in the temperature of the outside. So it's a thermal reservoir, as are lakes, oceans, and a large block of, say, copper or something like that. Thermal reservoir. Now let's get the second. This is where the turbine and the power cycle comes into effect. Here's the second statement of the second law, Kelvin Planck, that you will need to commit to memory, but I want you to restate it in your own words, maybe. Oh, you can restate it verbatim, that's fine, but I want you to understand what it says. Okay, here we go. Let's see if we can draw a little circle. I'm just trying to practice on you more than anything. Let's draw a little, not a very good one, is it? It is impossible for any system to operate in a thermodynamic cycle and deliver a net amount of energy by work to its surroundings while receiving energy by heat transfer from a single reservoir. All right, let's see if I can, here's it shows, all right, this is sort of this is like our boiler here. Actually, QH, yeah, this would be our boiler, which is a QH. Generally, by the way, TH and QH on a boiler, QH is the amount of heat transfer you pump into the boiler. TH is the effective high temperature. Normally, if we think of that as maybe the flame temperature of the natural gas or the temperature of the mean temperature inside the boiler. But it says just what I was telling you about in that little drawing I drew a while ago. All of the energy, thermal energy from the boiler transferred to the turbine, you can't get all of it out here as work. Some of that energy is going to be transferred out down here. And that's what happens in a turbine. We talked about it has an inlet and an outlet, and that outlet stream is full of energy. It's lost a lot of its energy, 35, 40%, but there's still a lot of energy left in that fluid when it leaves the turbine. And that has to be dealt with in your cycle too. So that's what the Kelvin Planck is saying. You can't take all this thermal energy and go right into the device and get work out from a single thermal reservoir. You can't take heat in and get work out. All right, let's take that off. You probably can't see this menu I'm doing. Okay. Let's take the annotate off. So, okay. All right, let's go to the next slide. By the way, I've already put homework assignment 5 out, and I chose problems that are not too difficult that illustrate some of the second law principles. And so you can get started on those right away whenever you get to it, but you need to do them. All right. Here's the entropy statement of the second law, and we haven't even studied entropy. So I probably, on a test on chapter 5, I couldn't ask you about entropy. But entropy, here's some things about entropy, and it's very important, as we'll see. Entropy is. Mass and energy are familiar examples of extensive properties. Well, energy per pound is an intensive property, but overall mass and energy are extensive, used in thermodynamics. Entropy is another important extensive property, unless you talk about specific energy, specific entropy, and that'd be entropy per pound mass or per kilogram or whatever. And how entropy is evaluated, we won't get to until chapter 6. Unlike mass and energy, which are conserved, entropy is produced within the system whenever non-idealities, that should, another way of saying it is whenever irreversibilities such as friction are present. In other words, entropy either can increase or decrease with heat transfer, but without heat transfer, entropy always increases. The entropy statement is, it is impossible for any system to operate in a way that entropy is destroyed. And again, you don't know what entropy is, so we'll figure it out later. Irreversibilities. These are things that happen in a process that keep you from converting 100% of that energy into work. And we've mentioned a lot of these. Friction is the one that most comes to mind as a mechanical engineer, such as myself. All right, one of the most important uses of the second law of thermodynamics is engineering is to determine the best theoretical performance of systems. And as you'll see, we do that with the Carnot efficiency. By comparing the actual performance with the best theoretical performance of a power cycle or refrigeration cycle or heat pump cycle, if we measure and calculate the performance of that cycle and compare it with the best possible cycle, we can get some insights on how good a job are we doing. And we can also tell if an inventor is trying to, if some inventor is trying to sell us a perpetual motion machine. We'll talk about that later. We come up with the best theoretical performance, and we evaluate that in terms of an idealized process. An idealized process is a process with no irreversibilities. There's no friction loss, there's no pressure loss, just like in an electric circuit. You have losses across resistors due to the voltage drop. In mechanical systems, you have losses of power, i.e. voltage, due to friction and pressure losses and other things like that. As you probably realize, those type losses keep an ideal process from being fully reversible. And those things like friction and pressure drop and voltage drop across the resistor that prevent you from converting 100% of heat energy into work, let's say, are called irreversibilities. Okay, here's some types of irreversibilities. I mentioned some. Heat transfer through a finite temperature difference. Unrestrained expansion of a gas, a liquid to a lower pressure. All right, let's talk about those first two. If we have a cylinder, try to imagine our cylinder with a piston in it, and it's got a gas inside that cylinder. And we've got it clamped with stops. We've got that lid on that cylinder clamped down, pushed down, and creating a pressure in that gas. But we've got some stops in there, say a rod pushed all the way across the piston, not allowing it to move. We've got it restrained, and there's a lot of energy inside that pressurized gas. If we pull that stop out, then that piston is going to move up in the bore and expand. Now, if I'm a big, strong guy and I come across and say, well, I'm going to push that piston back, down, and put those stops back in. Well, I can do that. And if I could do it such a way that no energy was lost, no friction, no heat transfer, it would be reversible. I could sit there all day strong enough, if I was strong enough, push it down, put the stops in, take the stops out, let it expand, so forth. But because of heat transfer to the surroundings from the cylinder, and because of friction inside the piston, I can keep doing it, but I lose a little energy every time. A little energy is lost. Those losses are due to irreversibilities. And that's mainly heat transfer through a finite temperature difference and the unrestrained expansion of the gas from a higher pressure to lower pressure. You just can't do those two without losing some energy. Spontaneous chemical reaction, that's an irreversible process. That's like the genie in the bottle, the spontaneous chemical reaction. Once that happens, once the genie gets out of the bottle, she's hard to get back in there, right? Spontaneous mixing of matter at different compositions of states. We won't get into that very much. The main one that I always dealt with as a mechanical design engineer was friction. And you will deal with that the same thing. You're in a power plant, or if you're designing, say, an electric motor, friction is going to be one of your worst enemies. And that's a friction, heat, those type heat transfers, those are examples of irreversibilities. Here's some more. Magnetic current flow through a resistor. Electric current flow through, excuse me. Magnetization or polarization with hysteresis. If you electricals, and I just barely remember this, if you look at the magnetization circuit, let's say you're measuring the field strength, two magnets, and as you pull them together, you get a current. If you were measuring field strength versus, say, the distance those two magnets are apart, you could plot that curve of magnetic field strength versus distance. And then you could start moving those magnets back together and plot it again, but they would be a big hysteresis. In other words, the one plot would not fall on top of the pulling apart plot would not fall anywhere close to the pushing it back together plot of magnetic flux. They would be a large hysteresis. That's an irreversibility. Elastic deformation is an irreversibility. If I have a beam, say in a structure, if I load it and keep within the elastic limit, then I can load it and unload it and load it and unload it, and it'll return to the same shape. But if I put a large enough load on a beam or any kind of mechanical device, it will eventually suffer some permanent deformation. That's inelastic deformation. That's hysteresis. No, it's not hysteresis. It's irreversibility. And I'm reading the last paragraph. All actual processes involve effects such as those listed, including naturally occurring processes and ones involving devices we construct, from the simplest mechanisms to the largest industrial plants. Irreversibilities are everywhere, but that doesn't mean we can take reversible thermodynamics and make some good calculations, and we'll know pretty close to what the best we can get, and those calculations are very important, even though we'll never get quite the performance or efficiencies that the calculations tell us we'll get. Okay, so I think I made it clear that a reversible process is a theoretical process. It's very useful to study reversible processes because a measure of how of their irreversibilities is a good statement on the efficiency of that process, and the efficiency can't ever be 100%. All right. Irreversible and reversible. The reversible process is a theoretical, can never achieve process. It's very useful for us to analyze. An irreversible process is a real world process. All right, I'm going to read a little to you. During a process of a system, irreversible may be present within the system, within its surroundings, within both the system and its surroundings. That piston cylinder that we let expand, it had friction that occurred inside the system, and then it had heat transfer due to that friction going to outside the system, to its surroundings. Now, this doesn't take a genius to state the next sentence or bullet point. A process is irreversible when irreversibilities are present within the system and or its surroundings. Yes, that's true, but it's not exactly a profound statement. All actual processes are irreversible. True. A process is reversible when no irreversibilities are present within the system and its surrounding. Another not so profound statement, but true. This type of process, a reversible process, is fully idealized. It never really happens, but it's very worthwhile to study because we can get some very useful real world limits on what kind of efficiencies we can get out of real systems we build. Here's another profound statement. A process is internally reversible when no irreversibilities are present within the system. Sounds sort of like government, what do you call it? Gobbledygook or something. I don't know why I can't think of that word. Gobbledygook. Irreversible may be present within the surroundings, however. An internally reversible process is a quasi-equilibrium process. And if you remember, when we say quasi-equilibrium, that's when we imagine a process going from state one to state two in small little steps. And after each small step, say we go from process 1 to 2 and say 5,000 steps. Well, after each, that's the way we can imagine it. Well, after each one of those little steps, everything becomes equilibrium, and then we go to the next step. That's what we call that's the quasi-equilibrium process. Okay, here's an example of an internally reversible process. All right, we've got our little cylinder here and we've got liquid water in it. And looks like right there. We'll be adding some heat, and this cylinder here is free to expand, by the way. And the walls are frictionless. They seal tightly, 100% seal, don't let water out, but they're frictionless. Now, if you could design a piston like that, you could probably become a very wealthy person because they don't exist, but they're useful for illustrative purposes. Okay, so we start adding heat, and some of the liquid water becomes water vapor, and that's a mixture. And if we look at this mixture here, about 30% of the volume is vapor, and say 70% is water. Let me go that about, looks like maybe 35% of this is liquid water, and about 65% by volume is water vapor. Now by mass, water vapor, the specific volume is so large, so many cubic feet per every pound, or so many meters for every kilogram, that that's probably a quality right there of, I'd say, probably 99%. In other words, of this liquid volume, well, you look and see about maybe, I don't know, just looking at maybe 10% of the water is converted by mass. So that'd be a quality of this mixture of 90%. Is that right? No, no, it would be 10%. It's mostly, no, 90% is right. 90%. Let me think of that. I said that wrong. No, the quality is 10% because only 10% of the mixture by mass is water vapor. Anyway, sort of beside the point. But now if we keep adding heat, all of this liquid water is going to turn into water vapor, and we have what we would call saturated vapor right here. For a system enclosing the water, there are no internal irreversibilities. Okay, what he said, if we add the heat out here and there's no friction in here, inside here, there's no irreversibilities. We said there's no friction, no leakage, but outside there would be irreversibilities because we have to add heat to get this water to evaporate. And we're adding heat in here, and there's some heat going to be conducted out through the walls of that cylinder. And that is an externally irreversible. So if we look at this whole thing, let's draw a circle around it. Let me find my annotate pen here. You can't see me pick it up. Let's draw a circle around that. Not exactly a good circle. Internally here, that is a reversible process. Externally, it's irreversible because there's heat transfer taking place. And once the heat comes out of the cylinder out in the air, we can't push it right back in without expending some other kind of energy. All right, let's undo that. And let's annotate. Where's the annotate? I can't find it. Oh, here it is. Sorry. All right. Now I'm going to glance at the share. Make sure you're still seeing what you should be seeing. Yep. According to what I say you are. Okay. So, by the way, this will get more interesting. Not a lot more, but more. Okay, here's an analytical form of the Kelvin-Planck statement. For any system undergoing a thermodynamic cycle while exchanging energy by heat transfer from a single thermal reservoir, the net work out of the cycle can only be negative or zero, never positive. The net work. So the work now, this is the work of the cycle. That's really a bit sort of hard to see here. But what that means, if we're transferring heat from a hot body or from one thermal reservoir, uh, we cannot roll up this. We can't roll it up. We can't create network to roll it up. This is a little hard to understand because I just gave you the illustration about the turbine, but this is not exactly the same situation. I'll have to explain that better to you later. But all right. So if the worker's cycle would have to be negative, uh, it theoretically could be zero, but real, if irreversibilities are possible, it's going to be greater, less than zero. I'm trying to think of a good example. Doesn't one come to mind? Doesn't one come to mind yet? Okay, we'll revisit that. All right, now we're beginning to get into something that's a little more interesting. And I made up some drawings. They're very crude drawings that try to illustrate some of this. All right. So if we've got, all right, let's see, application to power cycles interacting with two thermal reservoirs. All right, I'm going to show you that our power cycle does interact with two reservoirs. A QH reservoir producing where heat is thrust into the system, such in the boiler, and then a QC or Q cold reservoir, such as cooling water or an evaporator. And in that case, the efficiency of the cycle is QH minus QC, which is the work of the cycle, divided by QH. Now that's exactly what the efficiency equation is for the thermal efficiency for a power generating system. The work of the cycle over QH. And we know that a work of a cycle is going to be negative because, no, it's not either, is it? We're getting positive. The work of the cycle is going to be, this is going to be a positive number because we're getting work out of the turbine. QH is going to be a positive number because that's positive heat transfer. Okay, so you get a nice positive over positive. It wouldn't matter, as we'll see later, it's the absolute value of the ratio. But these are, for a power cycle, that the work's positive, that's the turbine work, that's the pump work. And we'll see the system, we'll see a schematic shortly. Over the QH, which is the work which is the heat inflow from the high temperature reservoir. Now, since QH, work of the cycle, is by the way, the reason that the work of the cycle is QH minus QC, maybe I ought to try to illustrate that on my fancy sketch here. All right, there's an equation. They used to teach thermodynamics. I don't think. When you're looking at a cycle, now this is the whole cycle, like the power generation cycle, this would be going through the whole cycle. You can say that the sum, okay, I got to pick me a pen here. There's my, oh, it's cut off, isn't it? Oh, it cut off on me. My pad cut off. Now it's back alive. It woke up. Okay, good. Way to go, pad. All right, let's. Let's eraser. All right, let's use my pen. You see how bad I am at this tablet. select eraser. Okay. In a cycle, and I'll gotta select a pen. We can say let me select that pen. I don't know. I do know. I'm glad you can't see my hand. I've got the pen upside down. I can't say I just did that where y'all would see if you caught me in an area. All right, I got the pen right now. I'll be able to write with it, I predict. The sum of the heat transfers in a cycle, the sum of all the heat transfers is equal to the sum of all the works. That's always true for a cycle. The sum of the heat transfer is equal to sum. We used to write that. Another way you can write that, if you want to make it look more mathematical, is say the cyclic integral of dq is equal to the cyclic integral. Now they don't use a d, they use a delta work. That should be a delta over there. But what that really means in a steady flow process like we study, as the sum of the heat transfers is equal to the sum of the work. All right, let's see if I can get back to PowerPoint. I don't want to minimize anything. Click right here. Okay, very good, Larry. Now, we're going to look at these in a little more detail in a minute on my sketch. Now, for a refrigeration and heat pump cycle, you see with this little, what we call it, what's the term? Can't think I will in a minute. Abstract. Got this little abstract system here. We've got a system in here, and it's actually able to pull heat out of this cold air. This would be like the room we're trying to air condition, the building we're trying to air condition, or the freezer we're trying to freeze the food. This would be that area. We're pulling heat out of there, and we got this cycle here. And then we're rejecting heat out to the outside. In a refrigerator, you're actually rejecting heat to the inside of your house. Yes, a refrigerator running properly tends to heat up your house, but it's generating, this heat level it's generating is taken care of by your air conditioner, and you're able to maintain a constant, nice temperature. Now, if it's a HVAC air conditioning system, it is indeed taking heat away out of your conditioned space and literally pumping it out against the second law, sort of, to a hotter space. But it has to be a cycle to do that. This is a refrigeration cycle here. Well, no, it depends on how you look at it. All right, let's look at it. This is inside the house. This is outside. So we're trying to cool the inside of the house. How do we do that? We pull heat out into our cycle. We store it in the fluid, and the fluid goes through some processes and eventually rejects that heat outside. That is an air conditioning cycle. And for an air conditioning, or by the way, for refrigeration, air conditioning, air conditioning is just a special type of refrigeration. the actual definition is all of the air conditioning, freezers, they're all refrigeration cycles, different types. Just depends on what kind of temperatures you're looking at. All right, we define this term called beta. And the way we measure the performance of a refrigeration system is by beta. And the beta is equal to what you're trying to do. You're trying to cool. You're trying to create this cooling effect. So that's what you want. But to get that, you have to put this work in. That's what you don't want to do, but you got to do. So beta is the ratio of the cooling energy you get to the work energy you put in. And most always, this work energy is electrical energy into an electric motor to drive the compressor. There are also other smaller motors in the air conditioning system, such as fan motors. Yeah, fan motors. There's two or three fan motors that run, but these consume about less than a horsepower all added together, whereas the compressor may be consuming 20, 30, 40, 50 horsepower. Now, the work of the cycle, we know the work of the cycle is equal to the heat transfer of the cycle. So this cycle receives a QC and gives off a QH. So the heat transfer, net heat transfer is QH minus QC. And now we use the arrows as we sort of drop our sign, not really, but when we look at these type abstract diagrams we're going to be looking at for a while, we sort of drop the idea of work out is positive, work in is negative. We really don't, but we start using these arrows. Here's what I mean. When writing this equation here, work of the cycle QH minus QH, we take, that's not right, is it? All right, this we're actually taking the larger one, QH minus the smaller one, and that's equal to the work of the cycle. Actually, if we use our definition of work and heat, it'd still come out right. We would write the work of the cycle is equal to QC is the plus heat coming in. There's plus in our definition. QH is the plus going out, so it'd be QC minus QH. And it would be negative. And the work of this cycle is energy into a device, into the cycle is negative energy, negative work. So they're just shifting around these to get a positive number, and they're showing the work in. They're showing it in the right direction, but they got a work cycle that's positive. You'll work a few of these and you'll get, don't let this confuse you. It will now, I know. But as you work a few and you look at these diagrams, it'll start making sense. I used to teach this, which I think is the better way, as the work of the cycle is equal to QH plus QC. And then you define QC, whether it's positive or negative. This would be a positive, this would be a negative. You put them in and you get the right answer. But that's not the way the books do it, so I'm going to follow the book. We'll see, don't get too excited. Beta, the performance, is called COP, coefficient of performance, COP, beta. Beta goes to an air conditioning or refrigeration system. Is the cooling amount of energy you're taking out as cooling divided by the amount of energy you have to put in as work, which is also equal to the QH minus QC. Now, beta, if you happen to get a minus sign for one of these and you got the right numbers, just call beta a positive. Beta is always a positive. If it makes you feel better, you could put in the absolute value sign here. Oops, hold on. Okay. Yeah, you would just put an absolute value. All right, now let's look at a heat pump. Heat pump does exactly the same thing except you flip-flop. Instead of flip-flopping, let me get rid of that pen. Annotate. Okay. Instead of flip-flopping, and we'll see this later, in a heat pump, you're trying to heat an area. So if you're trying to heat a house with a heat pump, now this becomes the inside of the house. Now, obviously, you don't switch inside and outside of your house. They stay the same. But in this diagram, he's sort of doing that for illustrative purposes. All right, after I go through this, I'm going to show you some sketches I made a couple of years ago I think make more sense. By the way, you know you can stop this video at any time you get tired. I may try to cover all these slides at this one sitting. I don't know, probably not. Let's see how many I've got to do. I'm on 23. No, I'm not going to finish. I think I'll go to I think I'll do another couple of slides and, well, we'll see where. All right. So, see what the next slide is. All right. Okay, he's got some conclusions here, which are pretty good. Let me erase this. It's pretty slick, isn't it? Except I can't ever remember to take. All right. By applying the Kevin Planck statement of the second law, three conclusions can be drawn. For a refrigeration cycle, for the refrigeration effect to occur, a network input is required. Accordingly, the coefficient of performance must always be finite in value. Let's go back and look at this. What that means is we're actually taking heat from a cold body and putting it onto a hot body. We're making heat flow uphill. Kevin Planck says you can't do that without putting some work in, essentially is what it says, and that's what we have to do. We have to put an amount of work theoretically equal to QH minus QC to get it done. And so this always is a pretty big number. So that means you're never going to get a beta of infinity. We'll actually see the limitations on beta later. And same, by the way, gamma is for a heat pump. I don't think did I finish a heat pump? Oh, anyway, a heat pump, what it does, I think I'm miscombobulated. Heat pump, this would be the area you want to heat. It actually pulls heat from a cold outside. Say it's 40 degrees outside and you want it 70 degrees inside. Well, it's actually able to absorb some heat from outside, even though it's 40 degrees. And it does this because its fluid is colder than the outside air. The fluid is, say, 35 degrees Fahrenheit, and the outside is 40, so it's able to pull some heat in from the outside and store it in the fluid. Then the fluid is compressed, goes into an condenser, compressed by a compressor, goes through a condenser, and now it's hotter than the inside, so you're able to transfer heat into the inside. So a heat pump is just pumping heat from cold to hot, and a refrigeration cycle does the same thing. But here's the difference. In a heat pump, the work you put into the compressor actually goes in to the heat in the fluid and comes out in the area you're trying to heat. In other words, you're able to use the work you put in, energy you put in to run the compressor as part of the energy to heat. That's really neat. The problem is practical in that if it gets cold enough outside, you can no longer pull heat. You can no longer pull the heat out of it. It gets so cold, your fluid is chemically limited to how cold you can get it. It's also limited. You don't want to get your coils below 32 degrees outside, or it's going to be hard to keep frost off of them because there's always moisture in the air, even in the wintertime, although it'll be less than the summertime. There's plenty of moisture to form frost on your coils outside. And so 32 degrees, it's actually about 35 is as low as a heat pump could operate. If it were true that a heat pump could operate at very low temperatures outside, it'd be a wonderful invention because you could take all of this work you put into the compressor and turn it into nice heat to heat your house. As it turns in, you can't quite do that. Okay, and the gamma for a heat pump, look, instead of QC, it's the same type of equation, but now it's QH. Because that's what we want. We want heat to heat our house or heat whatever you're trying to heat. So that ends up on the numerator in the work of the cycle. And that's the way it goes. Now it said Kelvin Planck. For refrigeration effect to occur, net amount of work is input. You got to put work into it. You got to have that compression. Two other corollaries are the coefficient of performance of an irreversible refrigeration cycle is always less than the coefficient of performance of a reversible refrigeration cycle between the same two temperature limits. We'll see more about this later. A reversible refrigeration cycle, all reversible refrigeration cycles operating between the same two thermal reservoirs have the same coefficient of performance if they're reversible. All three conclusions also apply to a system undergoing a heat pump cycle between hot and cold reservoirs. All right, I think we'll stop right there. And I'm going to go a little further in order to try to make things a little less confusing. All right, we'll start on slide 27. I'll write that down. Slide 27. All right, let's look at some of these diagrams I drew up. Let's look at the power cycle here. See if I can make that a little bigger for you. Here's our power cycle, very basic power cycle. We got the four elements of it: the turbine, a condenser, a pump, and a boiler. Here's how they operate. From a high temperature reservoir, and this is sort of a abstraction, the reservoir in the way I look at it in say a just wonder if I'm still recording. Yeah, I think I'm still recording. Okay. The QH, the TH, the temperature of the reservoir that you're drawing QH from, would be your boiler temperature. That would also be close to your flame temperature, but it's probably again, these things are not concrete, but I would consider TH my boiler temperature. All right. My TC of the cold reservoir is going to be generally cooling water flowing through this condenser. And that cooling water also is cooled, the flow of cooling water through the condenser is cooled by cooling towers, probably. So what the cycle is doing, it's getting heat in from a hot thermal reservoir at a temperature of TH. It's getting QH from TH. By the way, you'll see me use a lowercase, uppercase, and lowercase h sometimes, but don't let that, it's the same thing. But you're getting in a QH, you're putting it in the boiler. And that turns that high pressure water into high pressure steam. It packs a lot of energy in that steam. Goes through the turbine. As you know, if QH is 100, we're not going to get 100 units of work out of the turbine. We're going to get 35 or maybe at the most 40. So that leaves 60 units of energy still in this fluid. And that's what that statement says. I think that's the Kelvin Planck. You just can't take heat from a high temperature reservoir and convert it all into work. Can't do it. Got to have more of the cycle to it. Here's the rest of the cycle. Once it comes out of the turbine as generally almost saturated vapor, there can be, turbines don't like to run on a lot of vapor, a lot of water. They want steam to run properly, kind of like a compressor. So when the fluid coming out will generally be all vapor or 95% vapor or more. Then it goes into the condenser. The condenser takes this vapor, mostly vapor, and converts it into liquid. And these are heat exchangers, the boiler and the condenser. They generally can be said to operate at constant pressure. So you go constant pressure through the condenser, but you change states from a vapor to a fluid, a low pressure, fairly low temperature fluid. Now you got to get it up to the higher pressure of the boiler, so you have to go through a pump. Pumps it up. It enters the boiler as a high pressure liquid, and the whole process continues. Now here's the TV diagrams of these processes. This is the Carnot process. The Carnot cycle, you never get into the superheated range. Your TH is always the saturation temperature. So in the Carnot cycle, you take, all right, you come out of your boiler as saturated vapor, and you go down through your turbine, then turn it into a liquid to the condenser and pump it back up. The reason the Carnot cycle is important, even though you don't actually do that in the real world, in a real cycle, you want to heat out of you, is because Carnot showed mathematically that this type of cycle, the efficiency cannot be greater than the Carnot efficiency. And the Carnot efficiency is just 1 minus TC in absolute temperature over TH in absolute temperature. So let's calculate one. Let's say I had a TH of 600 degrees Kelvin, and a TC or TC would be 273, maybe 300. So 1 minus TC, which is 300 over 600. That's 1 minus 0.5 or 0.5 or 50%. So if I've got a device here operating between a TH of 600 degrees, maybe I ought to try to show that on my board. All right, see if my pen's gone to sleep again. Wake up, pen. Wake up. Now it woke up. Okay. So the Carnot efficiency is equal to 1 minus TH, the temperature of your high Nope, that's a T. Is it TC or TH? TC2. It's got to be TC, isn't it? All right, let's turn this thing upside down. TC over TH. In degrees Kelvin or Rankine. So that's 1 minus. Now, I've seen temperatures of 600 degrees all the time, probably higher. Let's say, all right, okay, sorry again. TC is generally around ambient temperature, a little above. Ambient temperature is about 25 or so degrees C. So that's around 300 Kelvin. And I've seen temperatures of 650. So the best efficiency I can get between those two temperatures, I have to get my, I don't have my phone handy. Let's see. I just have to pull up a spreadsheet. You probably can't see this. You don't see this spreadsheet, but I'm going to pull it up and divide what? 300 divided by 650. That's 0.46. So I should be back to where you were. Make sure. Okay, we're still with each other. All right, so 1 minus 0.46 is 0.54. So that's 0.5. Well, see, this is real. It's a lot harder than you think it is. R and as a percentage, 54%. So if somebody is selling you a new power plant system and they tell you they're going to operate between 650 and 300 Kelvin, and they're going to guarantee you a 60% efficiency, then you would call them a liar. You wouldn't pay them any money. What if they said 54%? Well, that's possible. That would be what we would call a reversible process. If the efficiency were 54%, that is a reversible process. We know we never can quite get there. If the efficiency is greater than 54%, it is impossible. If efficiency is less than 54%, it is possible. So that's your three outcomes you can have when you analyze a system. It can be either impossible based on the Carnot temperature efficiency. It can be reversible if it's exactly equal to the Carnot efficiency, or it can be possible. All right. Let's see if I can find my slides again. All right. Okay. No, that's not what I was working on here. So that's the Carnot efficiency based on temperatures. Here's the actual efficiency based on actual values or measurements. It's the net work over QH. And that's the work of the turbine minus work of the pump. That's the net work. Now, if we use our definition of work out as positive, work in as negative, we're going to get a negative number here. And if we use our definition of QH coming in, that's positive. We're going to get a negative number over a positive. Well, just put the absolute value because we're looking for a ratio. That's all we, but it is also equal to QH minus QC over QH. And again, signs are not so important here, but you got to remember these cannot have the same sign. They have the opposite sign. If we use our definition, this is heat in, so QH is positive.
QC is heat out, so QC is negative. So you'd get a positive number over a positive. If we use our definition, we'd get work of the turbine as positive. We'd get work of the pump as negative. We algebraically compare those, we get a positive number because the turbine work is 100 times at least greater than the pump work. And we divide it by QH. So a positive over a positive gives us a positive. So that's pretty straightforward. Now here's the Carnot cycle. Again, he doesn't go into the superheated range. He stays right on TH. I'm sorry, I'm going the wrong way. He goes through the evaporator at constant pressure, constant TH, goes down here and hits TC and PC, then goes back over here to saturated liquid, pumps it up to a high pressure saturated liquid. No, a high pressure liquid. It goes through constant pressure here down to here. And that's where the Carnot envisioned this cycle, and he was able to prove mathematically that with that type cycle, this is the best efficiency you can get. You can't get any better. It's impossible. So now we go to the real cycle, the basic cycle, and let's explain it. Now, by the way, you guys stop when you want to and restart. Now, I'm on a roll here, so hopefully I don't get this. Hopefully it's recording and I can figure out how to save it and get it to YouTube. If I can't, I'm going to be very disappointed. Okay. Yeah, let me look at y'all still hanging in there, right? Everything's good. All right. All right, here's a real cycle. Yeah. Can't quite. Let's see. Let's do a control minus here and get the. All right, there's a graph, there's a cycle, and here's the TV diagram. This will be the last chapter we'll use TV. We'll start using TS later, but you haven't had entropy yet, so can't use that now. Okay. Let's take this. We pumped up this liquid from our pump into this pressure right here. This is a constant pressure line. It's a very relatively high pressure. Like I said, it might be 100 bars, which would be 100 times 50. That'd be 1,500 psi. Actually, they're getting higher pressures. And by the way, the higher the pressure, the higher the temperature, the more energy you get into your fluid, the more you can get out of the turbine. But you're limited by the physics of water. Trying to get it super hot. You can get it really, really hot though. But more important than limitations, there's the maximum temperatures that boiler materials and turbine materials can withstand. So there is a practical limit on maximum temperature, just like with a heat pump. There's a practical limit on how cold the temperature outside can get, and the heat pump continue to actually function properly. So this is a constant pressure here, and let's say some typical values. Let's say 2,000 psi. Let's say 3,000 psi. That's on the high limit. That would be about 200 bar. You know, a bar is 14.5 psi or thereabouts. I just use 15 to round it. So I say in my mind, a bar is 15 psi. So 3,000 psi divided by 15, that's 200 bar or 20 megapascals. That's a very high pressure, about as high as you get. But we pump that fluid, that liquid water up to this high pressure, heat it through the boiler and heat it out into the superheated. This is really high heat here. It's still the same. It's on a constant pressure line, but then you see the temperature is way higher than here. So it's really hot. That's at state one. Then we go through the turbine. This is the expansion process through the turbine. And now we hit the low pressure coming out of the turbine. Well, I take that back. I think I said it's really at high temperature. It's really pretty low temperature, isn't it? So I guess I was wrong about that. But there's still a lot of energy in the fluid. So, okay. low temperature, low pressure. And by the way, this low pressure, typically a bar or less, say a half a bar. So we're going from, what did I say, 200 bar down to less than a half a bar through the turbine. A lot of pressure drop, isn't it? Get a lot of energy out of it. But if we look at the enthalpy here at 2 versus 1, there's still a lot of energy left in this fluid. Now we go through the condenser and we condense it. We convert into mostly vapor. We follow along this line by removing heat, and we eventually get it to all liquid, because a pump can't pump vapor. Once we get it all liquid, we send it into this pump, and it pumps it up to the pressure of the evaporator. So we basically have a high pressure, a pH, and a low pressure, a PL. Now, what is the TH for this situation? That's a good question. The boiler temperature, you could readily see, is whatever this saturation temperature is. It may be 600 degrees, but we're heating it up here to 800. So effectively, what is TH? Well, I have to think about that. I think I would call TH this, whatever this temperature is up here. Clearly, TL is this temperature, or TC is this temperature. All right. But there's the cycles. First, now let's look at a air conditioning cycle. Now this is the diagram, like I didn't point this out. The way he draws those diagrams, let me see if I can take a shot at that in the text. All right, I need to get my OneNote going. Pen, are you still alive? Are you still awake? Yep, he's awake. So let's go up here and pick the big eraser. Come on. Come on, Pen. Let's get the large eraser. Oh, we could use a lasso, right? Why didn't y'all tell me that? Because you can't interact with me is one reason, right? I'm going to move this up. Well, I got a whole bunch of stuff. Let's get rid of some of that. Lasso it. Yeah. Heck. Try again. When I do it with the mouse, I get a rectangle, but I seem to be able to handle that better, don't I? Let's get rid of this too. Now I forgot what I was doing this for. Oh, crap. All right, you got to keep your cursor within the bounds. Okay. All right, here goes. This is going to be a bad looking diagram, but here goes. The way they draw these type diagrams in the book. Whoops. Can't do that, Larry. You have to go back. Oops. You have to go back and select a pen to draw. I can't draw a straight line even following on those lines. Oops. I think he draws a circle. Then he draws a circle, the arrow to indicate there's a cycle going on in this circle. And let's draw it for the power cycle. This is T, use a small h, TH, QH. So QH flowing into our cycle. That's QH. Now coming out of the cycle, Q, C. And this is our thermal reservoir at TC. This is the thermal reservoir at TH. Again, this is probably that superheated temperature, maybe 700 degrees C. This will be like the temperature of cooling water, maybe 300 K. This might be the 650 K. But what I'm trying to illustrate here, there's his cycle. Now let's look how I draw it. Here's his cycle. Oh, I got to get back to that page. See, I take his circle and make it a square, and I actually draw the cycle in here, where it's pretty easy for you to see what's happening. QH is coming from that high temperature reservoir and going into this cycle, and it's entering at the boiler. Oh, I didn't draw the work out of it, did I? Let's do that. He draws, this case, we're getting, by the way, I changed color of these pens. He's getting work, call it net. And if we look at this cycle, this total cycle here, we know that the sum of the Q's got to equal the sum of the work. So we know algebraically now QH plus, QL, it's got to equal work net. Now let's say QH was 100 units. I'm sorry, that's QL right there. QL was 65 units. So work net would be 35 units. Could be kilowatts, megawatts, horsepower, whatever you. Now let's look at QH. In our definition, QH coming in is a plus. Plus 100. QL going out is a negative from the, when we're looking at our cycle as a system. I should have drawn, let me get fancy here. Erase, oops, I erased too much. Let's draw this cycle arrow in red. I leaned the pen too far. There's the cycle. Now let's go up here and change color and put that. That's the cycle boundary, that black, and the red is the actual cycle. So what was I saying? So if I want to get the work of the cycle, algebraically, this is the way I used to teach it. QH plus QL equal work net. And then when you put in the numbers, you would get the QH would be a positive, QL would be a negative, and work. But he puts them in, he puts it in, and there's Q, forgot to change the color of my pen. There's QH minus QL. He puts a minus sign already in there. Is equal to work net. Like I say, I used to teach it as QH plus QL equal work net, and let you assign the sign to these quantities depending on how they really were in the thermodynamic world. But the way they teach it in the book is to QH minus QL. So we'll stay with that. Just remember, when you work out a problem, you better not ever be adding QH and QL. If you add them together and get a big number, one of those numbers, you've got the wrong sign to. And you'll remember that work net is always the difference of these. Now, as far as the turbine, the work coming out is a positive, it's a W. And then, of course, the thermal efficiency, we already done that, is work net over QH. All right, let's go back there. No, that's not what I want to go back to. Yeah. All right, so that's now I'm going to cover these other two cyclones, then I'm going to quit. Okay, and hopefully all of this has been recording. Okay, well, let's look at the air conditioning cycle. Again, the way he draws it, let me erase it. See if my cursor works. Yeah. Very good. The way he draws it. Trying to get, whoops, I got to select a pen, don't I? We have our two reservoirs, and he used a big fat circle for the boundaries of the cycle. And that's changed. All right, we have I didn't leave much room here for my arrow. All right, that's QH. This is QL. This is TH. And I usually say this is outside of your house. Or if it's outside, yeah. If you're dealing with a freezer, it'd just be the room you're trying, where you have the freezer sitting. But a house, this would be inside. That's a D there. This would be TL. Let's change pen colors. Drawer cycle. And all of that inside there. Again, you'd come up with the same type equation. Sorry. That work net. And again, I used to write it as the algebraic sum of QH plus QL. And in this case, QH is going out, so it's negative, and QL is coming in, it's positive. So you'd get a difference between them. They do it, he does it, I believe now, as Q. He just goes ahead and puts a minus sign. But you work a few out and you'll see it. And he draws the work arrow. I got to disable gestures and I don't know how to do that yet. Work is going into the system. And the coefficient of performance for this type system, where you're cooling the inside, is beta. And that's equal, and I could write the absolute value if I wanted to, of what you want out, which is QC, cooling. That's called a refrigeration effect. By the way, that's the rating. You hear a unit is a 4-ton unit or a 2-ton unit. That's the QC, maximum QC that unit's capable. And we'll have a Q, whoops, sorry, turn my pen over. Work net. And as it turns out, this ratio is typically 3. Now, that's not efficiency now. That's a measure of performance. Now let's go back to, yeah. So I'm just showing you that little circle. That's what's in that circle. And it has four components: air conditioning or refrigeration system, at least a vapor, they call it a vapor compression cycle. And again, the reason it works is because you got a fluid that you can force into changes states. And when it changes states, when it flashes to a vapor, it pulls in a lot of heat. And when it condenses into from a gas to a liquid, it gives off a lot of heat. But here it is. Let's see, what do we call, here's the diagram of it. And again, the working fluid here is not water. It's a refrigerant, R134A or R410 or R22, R12, some of the old ones. But here's your QH going outside to TH. TH in a summer day, outside environment might be as hot as 100 degrees C. No, not that hot. Let's see, is that right? No. That's 212. No, if we get that hot, we're in trouble. The virus, all the viruses be dead, but we'll be dead also. No, it's about 100 degrees F, which is about 40 degrees C, somewhere around there. And inside, where you're trying to cool, is good cool temperature I like is about 74 degrees F, which is what? 74 minus 32 is 42. 42 divided by 1.8, that's about 23 degrees C. So here's where the only place you put the work in. Now in a real system, you got some air distribution fans and so forth, but here's where the major work goes. And by the way, as you know, you got an electric motor driving this compressor, and they're generally in one, let's see if this works on this. They're generally in a hermetic package, and you'll have your voltage coming in to the motor part, and that's typically 220 volts, 240 volts, and the amperage could be up 35, 40, 50 amps. There's a lot of power going in here. That's why it works. Okay. Now let's look. By the way, the diagram for these are really simple. Now here's your equations. Beta max, the maximum beta is based on the Carnot type of absolute temperatures, is TC over TH minus TC. Now let's look at some temperatures. If we had, we already said TC was about 27 degrees C. TH was about 40, so that's like 15. This difference here, and this C, what did we say was 27? No, that's not right. I think I may have that upside down. Do I? No, no. TC would be about, I'm right sketching down here on the, TC would be, say 74 degrees Fahrenheit, subtract 32 from that, that's 42 degrees. Then divide it by 1.8, that's about 25 degrees C. Okay, that's TC. TH is outside at 100 degrees Fahrenheit. That's 78 divided by 1.8. That's about 40. Let me get my spreadsheet back up. Anyway, let's call it 40. It could be 40. And so 40 minus 25, that's going to be 15. The difference doesn't matter if it's Kelvin or degrees, it's still 15 degrees for the denominator. The numerator is going to be TC, which is about 300. So beta max is going to be 300 divided by 15, which is 20. And that's and in some ways, this calculation is not that meaningful because in a real system, you don't get anywhere near 20. The 20 is the theoretical limit. If beta actual is 20, it's a reverse. It is a reversible process. If beta max is greater than 20, it's impossible. If beta max is less than 20, it's possible. Now the actual beta actual would be QC over the work of the cycle. Now let's look at the heat pump and we'll take a break, or I'm going to stop and finish later. When we go to heat pump, I'm going to keep the outside up here on the top and the inside down here on the bottom, where we can compare these diagrams more directly. We have exactly the same components, but here's what happens. We reverse the flow through the compressor. So instead of going counterclockwise, it's going clockwise through this circuit. So what does that mean? That means, remember, when we compress, we heat. So this is hot. It's hot vapor. And so we condense it here. So this is a hot vapor condenser, and it's hot. It's giving off heat. That's why it now performs a heating function inside your house. Now, we didn't change a thing except reverse the flow of the refrigerant. Now, on the outside of the house, here's the evaporator we used to use in a refrigeration circuit. It still does the same thing. It pulls in heat from the outside. Effectively, what it's doing is pulling in heat from the outside, storing it in the fluid, going through the compressor, which adds the work of the compressor, goes into the energy of the fluid, and you got all this hot energy and go through the condenser and you get a lot of heat out. That's the way a heat pump. Same components. It just reverses flow. And that just some practical, well, and if we look at the equations, they're very similar. This time you have TH over TH minus TC. And this is a gamma, supposed to be. Then the gamma is QH over the work of the cycle. And the work of the cycle is the difference between the heat transfers divided by the big heat transfer. QH is what you're looking for in a heat pump. And a refrigeration system, you remember it was QC. All right. So we just reverse the flow of this refrigerant using the same components. Now you have to design them properly where the evaporator, these are both just fancy heat exchangers and they can operate. One is the evaporator, one is condenser. And they can operate, go in reverse. And your cycle schematic is the same. I don't know if I think I went over that. Maybe it didn't. Anyway, the vapor cycle, refrigeration, the thermodynamic cycle is the same for both of them. You start here. Let's start going in. Where's state number one? This is it. Going into your compressor, coming out of your evaporator. Right here. This is a low pressure vapor. It goes through the compression process and comes out a high pressure, hot vapor. In fact, it's superheated, so it goes out here in the superheated region. Then it goes through the condenser and goes, now these are constant pressure process here, constant pressure process here. So it goes through the, all right, where did we take that? Okay. The condenser is right here. That's this process here now, and it's heating your outside with, and the interesting thing, it produces heat without any kind of flame, just gets the condenser hot. But again, it has the practical limitation of you're trying to pump heat inside here. So that means this outside temperature has to be higher than your fluid refrigerant temperature. And again, if the outside gets, say, 32 degrees or below, it's going to frost over the coils and make it really hard. You can get around that by not letting the air get to the coils. But what you can't get around is the minimum temperature you can get this refrigerant. It gets much below about 30 degrees. It just can't get any below. So that's a practical limitation. So just a little real world thing. How do they actually reverse this flow in the real world? All right. They do it with a switching valve. And I know you don't know hydraulic schematics, but this is a schematic of a switch. You don't turn the compressor one way for an air conditioner and another way for a heat pump. You do that, you're just going to end up with a basket full of failed parts. So what you do, these systems have a reversing valve under control of the control system. This shows both ports blocked. Well, you wouldn't have it in this. If I switch this down, this now becomes the effective valve in the output. And our flow is out of the compressor with the hot fluid into the condenser, through the evaporator. And again, this is outside, so we put the heat outside. We're sucking heat from the inside. So this is the refrigeration cycle here. Again, outside, inside, they remain outside and inside. Now, if we switch that valve, here's what the effective valve is on the outlet. So the high pressure, hot, superheated vapor coming out of the compressor now goes into the condenser, but the condenser is this inside heat exchanger. So now we're getting the hot air in the inside of the house. We're heating the house. Then we go back through. But that's just a little sketch showing you the practical. I'll post this online, or I'll post this on Moodle. I've already got your homework up. I'll already put slides on Moodle. You see these greens. I made these as corrections to try to get the signage to agree with the book. Again, I used to use algebraic sum, and let you figure out what was negative, which one of these heat transfers are negative, which one are positive. That's why you see the changes in green. By the way, making edits to a PDF document is murder. I could have just redrawn this whole thing, or either made it in a little CAD system. Again, I used to teach this as algebraic sum, and you figure out which is minus and plus, but the book doesn't do it that way. I don't think you'll have any trouble with it. Just got to remember that the work net is never these two added together. I mean, never the sum of this absolute value plus this value. It's always the difference between these two, the difference between the absolute value of these two. Don't stop. All right. Then now for the air conditioning system, we also have a Carnot gamma. And this time it's TH over TH minus TC. And what did we say TH was? TH was 600? No. TH was 40. Was about 310. And QC, what was about 300? No, it needs to be more than that. About a 15-degree difference. So if it was a 15-degree difference, it'd be, what, 300 over 15? So that's 20. So again, we never get close to a 20 beta, a gamma. All right, that's enough to chew on. Start on your homework. and I'll be seeing you later. If you have any questions, just call me, email me, or whatever, and I'll try to answer them. All right, I'm gonna shut the recording off. I hope all of you stay safe and don't have any problems with this. Um, what is it? COVID-19, coronavirus. All right, take care. Okay, I'm stopping the video now. Take care.